quite finished. I guess, was there a tougher question or a more challenging one, or is everything pretty easy? Ryan, anything challenging? No? How did you do this last one, 15? Because I'm pretty sure, I hope you, did you do it? Okay. Yeah, how did, Ryan, how did you do number 15A? Can I put you on the spot? So what do I get 1 over x plus 1 over 2x? Agreed? Okay. This might be worthwhile talking about because this is adding fractions, right? These are both rationals. So you just came out of a test where you had to do some rational work, and you did have to work a little bit with like finding LCDs, right? Which is kind of what you have to do when you combine fractions, correct? So what did you do from here, Ryan? Which is what? 2x, right? I guess. So then I have to, this needs a little bit of work, right? So I end up having to multiply by 2, right? I can't just multiply the bottom by 2. I have to multiply by 2 over 2, which is a form of 1, right? Because that doesn't change the proportion. So what, we got 2 over 2x plus 1 over 2x. And now I can add them, right, Ryan? So I get 2 plus 1 is 3 over 2x. Agreed? Okay, so we'd have to do the same thing with subtraction, right? I'd have 1 over x subtract 1 over 2x. I have to do the same thing. Adding and subtracting require common denominators. So I'd have 2 over 2x subtract 1 over 2x, leaving me with 1 over 2x. Which is interesting because it's one of the original functions, right? So what, and it also said give the domain. So can anyone help me out here? What would the domain of 3 over 2x be? What's the domain of this function? Now you could plug it into Desmos, I suppose, but do you, okay, so this is the new function. I mean, we could give it another name, but this is f plus g of x. We could call it h of x, I suppose, if we wanted to give it a new name. But this is the function 3 over 2x. Now you just came off a section dealing with, is that a rational function? Yeah, because it's got an x on the bottom. So, is there any shifting at all with this rational function? Are there any vertical or horizontal shifts? So then the domain and range should be the same as any rational, right? What's the domain of a regular rational function? X can be anything, right? Except for 0, right? Because this guy is just one of these guys, right? The set of, however, they're a bit stretched, right? So their curves aren't going to be right hugging the corner. They'll be a little kind of bent out. But as long as there are no asymptotes, only vertical and horizontal asymptotes will shift and change the domain and range, right? We'll shift them either sideways or up and down. These definitely affect the graph, but it just changes the bend. And this guy, same thing, right? It asks for the domain. So this is a regular rational, right? No asymptotes. So domain will still be all real numbers except not 0. Okay. Now, I don't know if you got to that last question, so I apologize if you didn't get a chance to do it, but I'll leave you with these guys, right? I think we can start talking about multiplication division. I'd rather push ahead now on the easy stuff and give us more time on exponents and logs and trig, which is where we need the extra time. So let's take a look. This is slightly more. I'm going to throw you a question. Please just respond, someone. Why do you think multiplication and division of functions would be more difficult or cause potential problems than add, subtract? More steps? Yeah. Which is what? A little more steps probably definitely more, multiplication of permissibles can be bigger, right? What about division? What causes problems anytime we have division? Maybe. Yeah, I guess division of polynomials. What do we always have to be cautious of when we have denominators? You cannot divide by 0, right? So again, we might have some non-permissible values. Because we're dealing with polynomials, right? What if my polynomial, what if my division statement became, well, for example, let's take these two. I'll leave them on the board. If I said find f of x over g of x, this is great because it ties in directly with the unit we were just talking about. Well, what is f of x over g of x? It's a simple thing. It's x squared plus 1 over x minus 7. Agree? That would be my division statement. This would be a rational function. You guys could graph this, actually, couldn't you? Right? We just came off that. Now, are there any non-permissible values? Yeah, x can't equal 7. So we're going to have to pay attention to that again. Always reinforcing the non-permissibles. What if this is, what if I flipped it? What if I said find g of x over f of x? Okay, I'm going to give you a minute. I want you to write the statement, and then I want you to state the non-permissibles. Okay? Okay, what would the statement be then? X minus 7 over x squared plus 1, right? You definitely could graph it. It'd be probably a weird one, but, and what are the non-permissibles? Yay, and why aren't there none? Because of the square, but it's not only the square, it's the square combined with the plus. There's nothing you could put in on the bottom that would make the bottom 0, or that would make the bottom negative, right? There's nothing, no value to put in. So that's the only layer. Like multiplication, definitely, like Adam was saying, they're longer because it takes longer to multiply like terms, right? You end up with bigger statements, and then division can cause problems because of those non-permissibles. So it's not going to be quite as quick as the add subtract, I think. So let's take a look. Let's read these notes, and then maybe we'll just do a couple of those bottom examples together. There's a few more examples you can see. So next, we'll work with multiplication and division. The process is the same, but using operations of multiply and divide. Similar to addition, the order that multiplication is listed does not affect the final answer, right? Multiplication and addition are really easy. I can add 3 plus 2 or 2 plus 3 and get 5. I can multiply 3 times 2 or 2 times 3 and get 5. But in subtraction, it matters who goes first, right? And also in division, we saw quite clearly that f divided by g is completely different than g divided by f. In multiplication, it wouldn't matter at all, right? Which one I put first. That's called commutative properties, right? Multiplication and addition both have it, and divide and subtract don't. So they're just saying, I don't know if I need to go over that. These are clearly itemized for you and noted quite nicely. Let's just look at the division though. It creates a rational function, which we've already talked about. Basically, when you're dividing two polynomials, you're going to create a rational function. A zero denominator is undefined, so we have to make sure we state our non-permissibles, or we're understanding of that. Since x plus, if we get this division statement, since x plus 5 can't equal 0, x is undefined, where x equals -5, that's their way of saying this means non-permissible values. That's just how they say it. X can't equal, -5. Okay. And again, you can always check back your answers, right, by substituting back in. So let's just take, I'll just take a couple of these. Let's just do this first one together. We've got f of x is 3 of x, g of x is x plus 3. Find f times g. you multiply them through, right? We get 3x squared plus 9x. Nothing exciting there, right? Again, it's going to involve multiplication of polynomials. Depending how big the polynomials are, like this is a monomial times a binomial, but you can see if they ever gave you a trie by a trie, that's pretty big, right? Trinomial by trinomial. Yeah.
How are they determining the value for the check? Like,
they're just picking they're just picking a random value.
as long as the statement is true.
Yeah, I had stated earlier, maybe it was just before you walked in, I always pick really small positive values like they did. Like you'd never pick negative 15 as a check, or you shouldn't, you could, but why would you, right? So pick a small positive value. They're just randomly picking a number, yeah. So this is another multiply. Now just to go, if I flip to the first page, I should have noted that first, your kind of table of contents here. They've got all the possible ways you could be given. Like you could be given a function just as a capital F and G. I've never seen that. You'll always be given your functions by our provincial standards and stuff. They'll either say f plus g of x or f of x plus g of x, right? These are the common things in Manitoba. Same here, right? F minus g all in brackets of x is the same as saying f of x minus g of x. Let's go down to the multiply. Everyone remember that dot hovering in the middle, right? Between, not on the bottom, but that's a multiplication symbol, the dot. So f times g of x is f of x times g of x. Or I mean, it could be this, right? F of x multiply, we could use the star, right? Everyone remembers that for multiplication. It could be the giant X, but it probably wouldn't be, but that's multiplication. And again, division, it can have the old-fashioned division statement. More often than not, you'd probably be given it to it in this form though, right? F of X over G of X. Okay, so just be comfortable with all the ways. So let's just look at this the first time we see division. This is my f of x statement. This is my g of x. Find f of x divided by g of x. So we just create the rational, but this is the part that we'll be looking for in assignments and tests, stating your non-permissibles, right? State any non-permissible values, okay? And here again, Eduardo, like you asked, they're just picking a number to check. And they're checking it in each statement. They're checking their F, they're checking their G, and then that allows them to do the division. They're just checking their work to make sure that their division statement was correct, right? Okay, does this look okay to you? Let's see what they did with, maybe it might be worthwhile to look at this square root one, because something I noticed on your radicals part of the test, there's a little, people had some problems with that. So let's see, if f of x is the root of x and g of x is the root of x squared plus x, find f times g of x. Okay. So we have our two radicals, the root of x times the root of x squared plus x. When you're multiplying radicals, basically the radical signs just merge. You can write the multiplication becomes just a multiplication under one radical sign, right? You can just, the radical signs merge and it just becomes x times x squared plus x, which would give us, it's kind of strange, but, x times x squared plus x. So what they did was, can you guys follow what they did from here to here?
Yeah, they did it and factored out the x squared.
Yeah. So they factored out, so basically I think they're missing a step here that you might want to include, because it's a little confusing, right? So let's do this. We're going to include one more step. So what would you do here? X times x squared is x cubed, and x times x is x squared. Okay, so at this stage, and this is, I know you did this in grade 11, because I'm helping people right now in grade 11 to do this kind of, to simplify it again. So what I do is, because I'm looking for the root and I have x squareds under here, I know I can simplify a little bit, because the more you can pull out of a radical, the better. So the GCF here, greatest common factor, is x squared, which is what they pulled out here, right? This is my GCF. So I took a x squared out of this term, leaves me with x squared. If I pull an x squared out of an x squared, I'm left with a 1. That's how they got the x squared times x plus 1, and therefore, maybe I'll include another step down here. So what they did is then they broke these two guys apart in a way. It was the root of x squared times the root of x plus 1, and the root of x squared just becomes x. That's how they got the x there. Okay? And then this is what I was left over with. So the root of x squared becomes x, and that leaves me with my x plus 1. Now, notice this is important too, because the radicand can't be less than 1, right? Because otherwise that would send the radicand into the negatives, and that's not possible. X must be greater than or equal to -1 to keep the radicand 0 or greater than 0. So again, stating the non-permissible values. All right, then they're just playing around. They gave you two statements, and then they're just getting you to find a real value. Do you want me to go over one of these? Sure. Do you want to? Let's do the one with fractions then. They're saying find f times h of 2/5. I think I might do it before. I prefer doing them separately, meaning I don't like this approach. What I do is I find f at 2/5, and then I end up multiplying it by h at 2/5. Just because the statements are smaller, and to me it just seems easier, then I don't necessarily, maybe don't even have to get into squares and stuff. So f at 2/5 is equal to, okay, so 3 times 2/5 squared minus 2/5. Okay, I'm just going to keep working across the page here. So squaring a fraction, 2 squared is 4, 5 squared is 25, minus 2/5. Remember how we multiply fractions? One underneath any whole number. That gives me 12 25ths. Subtract 2/5. And again, I need an LCD, right? So that'll be 12 25ths subtract, I have to multiply it by 5, so 10 25ths, which is 2 25ths. Yikes. Okay, so that was just one part of the question. Now I have to do the second part. Now this is interesting. It says h of x equals -3. That's it. What type of function is h of x? Linear. It's just boom, -3. So it doesn't matter what the x value is. I could put any x value in. The y is just going to be -3. So therefore, f of x times h of x is just going to give me 2 25ths times -3, which will be -6 25ths. Okay, so a little bit of fraction work. Obviously, they gave me a value that was a fraction, so you know you're going to have fractions potentially. Okay. Because this was a multiplication statement, there was nothing that was undefined here. There's no non-permissibles, right? Let's take a look at this one. We've got t and r. Find t divided by r at -1. Again, whatever your approach is, maybe you want to write your function first like they've done. T of x divided by r of x equals x squared over x squared minus 1. In order to state your non-permissibles, right, You probably have to factor things out, but x can't equal plus or minus 1, right? Okay, so let's just see. I've got x squared over x squared minus 1 at a value when x is negative 1. So I have negative 1 squared all over negative 1 squared minus 1, which equals 1 over 0, which is not possible. So we say undefined. Now, so they said find the value of the function at negative 1. This is the function. What type of function is this? Rational, right? So if the function is undefined when x is equal to negative 1, doesn't that mean this means the function is undefined at x equals negative 1. And what does pictorially, like on a graph, what happens at all the spots where a function is undefined? Holes or because negative 1 is a non-permissible value, right? What happens to our non-permissibles, right? So this means there's a hole or vertical asymptote at x equals negative 1, right? It's all kind of coming together, right, in a way? So what would this guy be? Would this be a hole or a vertical asymptote? I think asymptote 2, right, D? Yes. Because if we factored it, let's see, if I factor this properly, well, I'll do it on the board. X squared over x squared minus 1, this is what our function is. X squared over x squared minus 1, let's do a bit of a review here. This would give me x squared over x minus 1, x plus 1. Okay, no common factors, right? So I still have non-permissible values at x equals plus minus 1. No common factors, so they must be vertical asymptotes, right? At 1, x equals negative 1. Could you guys graph this if you have to? Take a piece of sketch paper, just do a real quick graph without even doing a grid. Do a real quick sketch of this guy. Even if you don't have a ruler, just do something like this. I already gave you 2 valuable pieces of info. Vertical asymptotes, you got 2 of them. I was pretty impressed by all your graphing rationals, by the way, for all your listing of the important info. Most people did a really good job of that. in no holes but vertical asymptotes. What's another important piece of info for rationals to kind of run through my checklist?
Horizontal asymptote.
Is there a horizontal asymptote? One? You would not get full marks for that. What's wrong? What do you not get marks for? Y equals. Okay, 'cause it's yeah. Because they're statements of lines, right? An asymptote is a line, so it has to say x equals or y equals. Okay, so after I get so I can sketch that in. Okay, so it's going to be this. This is my horizontal asymptote, y equals 1. I got my verticals. Okay, after, I guess, one more thing I usually run through is to see if there are any intercepts. So y-intercepts usually the easy guy to do. I put zeros in, so 0, right? And x-intercept, it has to be 0, right? If y-intercept 0 has to, let's see if I have any others though. 0 equals x squared over x squared minus 1. I do a cross multiply. I get 0 equals x squared. So the only intercept is going to be 0, right? Okay. So, let me go to it in red. So here's my intercept. So I think I know what's going on here. There's only one more interceptor, or there's only one interceptor. I'm pretty sure if I did a test point of a half, it would come down like this, right? Because graphs hug the vertical asymptotes and want to become them. They end up looking just like them. Okay? And then I have to figure out what's going on here. I'm pretty sure because I have all these x squareds that whatever happens on this side is probably going to be pretty much a mirror image. But I don't have any other info, so I guess I'm going to have to do the test point. So a test point at probably x equals 2. See if I can handle this late in the day. So I get a 4 over 3, so a little over 1. That just tells me if it's above or below the asymptote, right? So when x is 2, y is 1 and a little bit. So sure enough, it's going to be right here. And you know what? After all the work that we've done, I'm pretty sure I know what it does with verticals, right? It just hugs it, and then because this is a traditional rational, it's not one of those weird ones. Only the weird ones are going to cross horizontals. Okay, so I'm pretty sure the same thing's going to happen here. Like if I put a negative 2 in, I'm going to get the same values, right? Because of the squares. So if x equals negative 2, I'm still going to get 4/3. So I put a negative 2, 1 and a little bit. Okay, and everyone's asymptote work was pretty good. I just had one person on one graph do this. So tell me what the mistake is. Yeah, asymptotes never run away. They're always running towards. So don't do that. Okay? Alright, so there you go. How many people got something that resembled that? Good. That's basically a review of, a good third of your rational function work. So this function composition, one of the reasons it's after rationals is that when we're doing the division of two functions, they're going to end up in a rational, right? And you should be able to work with functions both ways, right? Just creating an algebra statement, but also be able to graph that algebra statement. So that's it. So just remember the non-permissibles. That will happen with rationals, and it'll also happen with radicals. We haven't spent as much time stating the radicals, but we always have to make sure we end up with positive numbers under a radical sign too. Let's see what this next page has for us. A division statement here, so they put fractions. So I would probably look this one over as well. I mean, I could do this one quick just because it involved a fraction, right? I find that students are most reluctant to work with fractions. So h of x divided by w, so I'd end up with this would be x squared minus 9 over 2x plus 6. And I'm dealing with a negative 1/2. So a negative 1/2 squared is 1/4, right? So I have 1/4 subtract 9 on the top, and then I have 2 times What's 2 times negative a half? Negative 1 plus 6. Okay, so on the bottom, my bottom's easy, right? Negative 1 plus 6 is 5. But I have this 1/4 minus 9 that I have to deal with, so I need LCDs. The LCD would be 4. So another way to represent the number 9, instead of it being 9 over 1, right now I'm going to have a 4 on the bottom. So what number with 4 on the bottom, what does my numerator have to be to resemble or to represent the number 9? What number divided by 4 is 9? 36, right? Okay. So then I got 1/4 minus 36/4, it's a negative 36/4 divided by 5, okay? Yeah, so we never leave, what happened here? I'm still good, right? Oh, they ended up factoring. I'm gonna do it the long way, I guess. We never leave. You don't have to simplify fractions in grade 12 for some reason. Like if you get 2/4, you don't have to simplify it to 1/2. However, when you have a stacked fraction, a complex fraction, you can't leave it in this form. You have to go further. So this becomes negative 36/4 times 1 over 5, right? Which gives us negative 36 over 20. Doing it this way allows you to simplify, right? I guess. Okay, so now, oh, sorry. Thank you. That's what you're trying to tell me, I mean. Okay, so that lets me simplify a lot easier, right? Okay, so at this stage, remember you can simplify fractions, any number on the top of a fraction statement. Like any top number can be simplified with any bottom number. So these two, if these could be simplified, I would, but they can't be. But these two guys share a common factor of 5. So 5 goes into 5 once, into 35 7 times. So I have negative 7 times 1 gives me negative 7 all over 4. Okay? So fractions are not going away. They're going to come back even stronger in the trig section. So that's why anytime we can play around with fractions, I want to take that opportunity to reinforce your fraction work and get you thinking about fractions again. Okay, so you can finish off the addition subtraction statement if you didn't finish it, and then I'm going to assign the next exercise 4.2 as well. So it involves the multiplication. Again, this is going to give you practice on polynomials and maybe a little bit of fraction work.